Now in this lecture we will see some specialized kind of learnings. We will start with this semi-supervised. So semi-supervised, also called weakly supervised learning, is when you have some data sets in which a part of the input data is labeled. So you have two kinds of labels here, purple and blue, and then some of the points are purple, some of the points are blue, but there are many other points that are unlabeled. And then the supervised part, so the blue and purple points, they are treated in the standard way, and they have some loss function associated to how well the network is predicting their labels, their true labels. But then you have the unlabeled part. So the unlabeled part, which are possible loss functions that have similar, that can deal with this unlabeled part. And this unlabeled part can be treated in this way. So you can add multiple losses. The first one is this consistency loss. This consistency loss tries to promote continuity by bringing the idea that similar points should have similar decodings. So for instance, let's say that you have an unlabeled input XU. You go through the network and you perturb a little this input vector. So the encoding or the embedding of these two vectors should be similar. So now you can measure the distance between the two embeddings, and you can try to minimize that distance for all the labels or for all the samples in the unlabeled part. The other one is this clustering. So this clustering, what tries to say is that you have some unlabeled samples. You make a prediction. So you predict what is the probability of having the class C given this label, and this is the entropy of all those predictions. So the prediction for a given for the same given input vector, and then what you are trying is to minimize that, saying the prediction should be somehow confident. So if you make a prediction about a point, that prediction cannot be very smooth, saying all labels are equally likely for this unlabeled example. The other one is this manifold. This manifold means that if you have two input vectors that are somehow that are closed in the input space, so you can construct kind of graph on the input space, so that input vectors that are close to each other, they are connected in the graph. So this wij will be a similarity function, and this similarity function, so it has to be such that if they are connected in the input space, the embeddings, they also have to be connected according to this one. So if they are very important, if the connection is very important, then this weight, this difference, cannot be very large. So this weight matrix, they are imposing some regularity in the input structure, in the output structure, in the embedding structure, and this is also called Laplacian regularization. We have also this transductive learning. So transductive learning is somehow trying to propagate the labels from the, the noun from the noun samples to the unlabeled samples. So here it is based on a graph, and this graph you have a similarity between. So this is labeled by similar. The graph is constructed by similarity between the input vectors, between the x. The y's are the labels that here are represented as red and green, and then for the unlabeled points, for instance 4 is an unlabeled point. So for each one of these unlabeled points you have to try to determine what is its label, and you do that by doing random walks. So you start from this label, from this sample, you do a random walk around, and then you count how many random walks end up in a node with a red label, how many end up in a node with a green label, and then you count, and then 4 is assumed to be red because there were more random walks ending in red node than in green node. Then you have this inductive learning. So inductive learning is trying to produce pseudo labels. So you have a small portion of the data that has true labels, and then you construct the first classifier just using the label data. Then you have lots of unlabeled data. You use this classifier to produce pseudo labels. These pseudo labels can be soft or can be hard. So then you will construct a new classifier. So this new classifier will have the originally labeled data, so this one, plus the pseudo labels coming from the unlabeled data. And these pseudo labels you can take just the more confident that you have. You may take all of them, or you can iterate multiple times here. So let's say that you take only the most confident. So with the most confident you have a new data set, you construct a new classifier, you do new predictions, and you use these new predictions again with the unlabeled data. You have new pseudo labels and you iterate this process. You can do that in another strategy. This strategy is called pseudo labels, and this strategy is called co-training. So in co-training you have label data and you split it into parts, so two halves of them. You have unlabeled data and again you split it in two, and then with this labeled data you train a classifier, you produce pseudo labels for this one, and you have these more confident predictions. You do the same with this one. So you have labeled data, you train a classifier. With this half of the unlabeled data you produce pseudo labels. You take the more confident predictions, and then with the more confident predictions of the second and the true label data here, you train your new classifier and you do the same with the second classifier, and again you can repeat this process. So this is called inductive learning. This one is also inductive learning. You can also do active learning. So active learning is you train your model with your label data, then you evaluate the unlabeled one, and then you ask for labels for some of the examples. So for instance, you can do uncertainty sampling. So select the samples that the model is most uncertain about. So you can measure the output of this soft label assignment, and then the ones that are more entropic, you can ask for the user for a label for it. Or diversity sampling. So select the samples that are most different from the already labeled ones. So I have here some labeled, and then I will take the ones from the unlabeled data that are more different, or this query by committee, where you use multiple models and select the samples where the committee members disagree the most. So this active learning will ask the user for new labels, but not for any random input data, but for some of them that are particularly difficult or interesting. Then we have also this curriculum learning. Curriculum learning is somehow you have a big data set. This data set you have to classify into easy examples, medium examples, hard examples, and then you will learn your model in a kind of structured way, in which you will first learn the easy ones, then the medium ones, then the hard ones. So somehow it resembles a bit like the active learning, in which you start from the easy ones and then you query your curriculum selection method given the current state of the knowledge, which are the examples that are considered to be more difficult or extremely difficult, and then you train your model with the new data. Here you have some flavors of this curriculum learning, this self-paced learning, balanced learning, or whatever. And so there are different flavors of this, choosing what to learn next. The last example that we will see is this reinforcement learning. Actually, we will cover it more in detail across the course. So in the next lectures, we will explore more this reinforcement learning in the context of neural networks. So the idea is that you have an agent, and this agent is a neural network. This agent has a state, and it has to produce an output that is an action. So this action can be seen as a soft labeling of what is the best action at this moment, and then this action will interact with the environment, and the environment will give you some reward that is a kind of loss function, or not loss function. It is the opposite. You want to maximize the reward rather than minimizing the loss. And so it will give you a reward, and it will update the current state. So for instance, here we have a robot. This robot has some environment that is fire and this tap with water. So if it moves, if the action is moving towards the fire, then it gets a loss, and then somehow the network has to learn that the best action is to take water to put out the fire. Okay, so we will see that in the next lectures. So reinforcement learning will be further explored.